to Pink Box and see what they have. They got a plain old twist. They got the old-fashioned donuts. They got a lot of cream-filled donuts. God, I've never seen so many donuts in my life. I don't even know what to get. They even got a watermelon donut and an Uncle Sam donut and a donut that looks like a hot dog. Well, I gotta have to think about this for a few minutes. Excuse me, sir. How many different kinds of donuts do you have here? Do you know? Let me count it. 12, 18. Okay, 33, 48, 63. I count 77. That's good enough. Close enough. Thank you. 77 different kinds of donuts. They had 77 different types of donuts in the shop, and I bought 12. And my question, which I'd like to try to answer tonight, is how many possible orders could I have made? At the beginning of the video, I showed you where I was last week. I went with my friend for Memorial Day weekend. I ended up purchasing a dozen donuts from Pink Box. They had 77 different types of donuts there. And so the question I'm answering is a specific question is how many possible combinations of a dozen donuts out of the 77 varieties that they had could have I chosen, assuming that there were at least a dozen of each variety available. I don't think there were, but we have to make a simplifying assumption, so let's just assume that. So that's a question I want to try to answer. So how do we answer this question? Well, this is a classic combinatorics problem, and here's a little cheat sheet. I guess if you were taking a class in combinatorics, you might have a cheat sheet like this, which you might be able to use on an exam or something. So, but we want to be looking at the entries on the right column here. There's two entries. So the top entry is just this is just what's called a binomial coefficient. N choose P. People also write it as C with an N superscript and P subscript. I guess they say CNP. And there's a formula for that. And by the way, what this is if you have N identical objects and you want to know how many possible the ways there are to choose exactly P out of those N objects. I guess the objects are identical, but they're distinguishable, which means we can number them all. So how many possible ways can we choose P out of the N distinguishable objects? Well, it turns out there's a formula for it. It's N choose P or CNP if you like. And there's even a formula for that. It's equal to N factorial divided by P factorial times N minus P quantity factorial. You can also get that. There's a lot of ways you can derive this formula. I'm not going to do it today. You can get it from Pascal's triangle, and there's other ways you can derive it. I did this in another video. So anyway, but that's not what we want for this problem. We want something else. We want to know how many possible ways there are to choose P objects from a collection of N different possible varieties of objects. And that's a different number. We write it here as CNP with a bar above it, CNP bar, I guess. And there's a formula for that. It turns out that CNP bar is equal to a binomial coefficient, Cn plus P minus 1 P, or if you like N plus P minus 1, choose P. So that's the formula. And I wrote it out again on this slide, and we can still write it in terms of the factorials. So you have a nice formula for it involving factorials. And so now we just have to plug in the numbers that we're using for this problem. And remember, there were 77 varieties. That's our N. So N is 77. P is 12. We're picking P 12 donuts. So P equals 12. So we have C bar 7712. And that's in terms of binomial coefficients, that's equal to C 8812. And then we can use a factorial formula for that. 88 factorial divided by 12 factorial times 76 factorial. Factorials, as you know, get very, very large. So this is a really, really large number. As a matter of fact, I calculated it on Wolfram Alpha. This is the answer. It's in the trillions. It's in the hundreds of trillions. It's equal to 205 trillion, 371 billion, 886,988,268. That's the total number of possible orders I could have made at Pink Box if I wanted exactly a dozen out of their
77 varieties. That's a huge number. I mean, uh, if I went back to pink box every day for the rest of my life, assuming I'm gonna live another 30 years or so, which I kind of doubt, but assuming I did, that means I'd be going back about 10,000 times. 10,000 is minuscule compared to this number. And even if I did that, I'm sure I wouldn't live another 30 years or 10,000 days because I'd get sick from all the donuts I've been eating. But anyway, you get the idea. It's an astronomical number. And, those are pretty common in combinatorics. A lot of times in combinatorics, you end up with huge, huge numbers. A lot bigger than you would expect. And I guess this is a case in point. But how do we derive this formula? I want to give a little explanation for the formula on the cheat sheet that we used. Well, here's my explanation. So I want to derive the formula for C bar n choose P that is equal to Cn plus P minus 1 choose P. How do we derive that? Well, it's not that hard. So here's how we do it. Remember, we're choosing P objects from a variety from n varieties, and we can convert that. We can convert one of our choices, one of our combinations, into a string of zeros and ones of length n plus p minus 1 with exactly p zeros and n minus 1 ones. How do we do that? Well, here's how we do it. So um, we here's how we make our string. So we go through each variety of donuts or objects in the general case. And if there's a total of p varieties, we number them from one to p. Or if we actually we, yeah we there's n varieties. We number them from one to n. And so for the first variety, we let p sub 1 be the number of objects in our set of variety 1, p2 the number of objects in our set of variety 2, all the way up to pn, number of objects in our variety n. And then what we do when we write down our string is we write a sequence of ones. We write, I guess, what is it? N1 ones followed by 0, then N2 twos followed by 0, or P1 ones followed by 0, P2 twos followed by 0. If any of these P's is equal to 0, which most of them are, we just don't write any ones. So that's how we do it. And you'll notice that when we're done, and then on the last step, we're writing down P sub N ones, but we don't follow that by a 0. So in the end, what we're left with is we're left with exactly p minus 1 zeros and n um, yeah, and ones, and that is a combination of n plus p minus 1 strings of zeros and ones. And you can think of, I mean, it's a unique one. You get a unique string like this for every possible combination. And what that means, you think about the zeros. So how many ways can you select the zeros? Or the ones rather. The ones correspond to the donuts. Well, there's exactly p ways to do that, or in the case of our donuts, 12. There's p ways to select the ones because there's a total of p ones, and there's going to be n minus 1 zeros. Yeah, yeah. So the answer we get is n plus p minus 1 choose p. That's how we derive this formula. Anyway, I guess that's the end of my talk. Thank you for watching. Long live math. Don't get sick on donuts. And I'll see you guys next time.